Get started. So we're going to hear sort of about Spark streaming, some of the programming techniques that you should know. And this is Gerard. He's been working at Lightbend for, he said, a couple hours at this point. And yeah, I think that this will be a great talk. I think I do sort of, I'll make the disclaimer, and I'm sure he will as well, that this is oriented towards Spark streaming and the DStream API, but I'm sure some of the lessons are really going to apply to structured streaming as well. So with that, let's give him a round of applause, and he'll go ahead and get started.
All right, thank you everybody, and thanks a lot for being here today, and I hope you're enjoying the summit so far. Today I want to talk to you about some techniques that we have collected over the years about Spark streaming and how to apply it in different scenarios and contexts. Some from very easy to, let's say, a more advanced techniques that you might want to apply, you want to add it to your toolkit, and take it out when you need it. This is me, senior software engineer at Lightbend as of today. This is my first working day. I've been involved in a community from Spark from early on. I adopted Spark in previous job in Spark 0.9, and I was also early on Spark streaming. Wrote one of the first tuning guides that was out there. And also be involved with the Cassandra community over the years. And you could find me sometimes contributing to Stack Overflow. So if you have questions, you can go there, and then I'll probably give you an answer. And some of the techniques I will be covering today is kind of summarizing what I really get, like high-frequency questions that people really don't fully get. And I wanted to summarize and put a kind of definitive answer here and provide it as, let's say, a guideline. I'm also the co-author of the Learning Spark Streaming together with Francois Garillo, partnered in crime in this crime scene. And we are also adding quite some content about structured streaming, and we'll probably change the title as well so it fits the content pretty nice. I'm jumping into the fast data platform, so that will be my project. I'll be contributing to all the streaming techniques, the streaming technologies in the fast data platform from Lightbend. This is a curated platform made out of all Apache open source projects that are pre-integrated for you, and it brings you high value on getting started really fast. And if you want to learn more about it, just come talking to me just after the talk. Okay, so what I want to do today is first get you all on the same floor. So we are kind of physically, but on Spark streaming, I'm going to touch on the model and operations very quickly so we can depart from the same level. And then I'm going to cover a few techniques. First, starting with how you do self-contained stream generation. Now, why would you like to do that? It's very, very handy to test quickly something, either on a unit test, but also to get your prototyping really quickly. So when you're talking streaming, we are also talking about external systems that are providing data, and not every day we have those up and running. And if we want to decouple that streaming generation from streaming consumption in a very quick way, you know, I have an idea, I want to test it out. There are a couple of techniques there that can help you out really quick in the same context. Second one is it's a very sought after technique. How do you refresh external data? How I get my database, my Cassandra tables, my Parquet files out there. I want to use them to enrich the data that is flowing through the system. I want to add those to the streaming data to make decisions, to make comparisons, to classify things, a number of use cases there. And there are a couple of caveats there when you are reading data from external source. I'm going to teach you or give you some tools how to refresh the external data, either on a time-based interval or on a trigger-based one. And then the next one is about structured streaming. We are hearing a lot about structured streaming in this morning's keynote. It's very exciting. It's moving really in a great direction, lowering actually the entry point to work with streams in Spark, making it accessible for all of us. But today, we are in that point where, oh, I still have some Spark streaming jobs running. How could I make sure that if I migrate to structured streaming tomorrow, I can still take my code, port my code one to the other, or even try out both at the same time. You can write some code in certain ways that we can run it in Spark streaming and in structured streaming. And then the two last ones, keeping arbitrary state. So we have map with state and some other state manipulations in Spark, in Spark streaming. And this one is when you want to go beyond that, when you want to go beyond that key-based state management. Last but not least, and I hope we get there on time, we'll talk about probabilistic accumulators and how can you plug that into your stream to learn about your data flows. And learn, I mean, in terms of counting, in terms of extracting some key indicators from your data using the accumulator API that Spark provides us. I'm going to go really quick through this. Spark streaming refresher, how this thing works. This is a well-known Spark streaming architecture form. We have a set of sources of data. Those sources of data are providing a stream of data that comes into the context of a Spark streaming. The task of a Spark streaming is putting those into blocks. And those blocks then are becoming the RDDs at a certain point in time. So we are all talking about this micro-batch architecture where chunks of data are backed together and then are pushed down to the Apache Spark engine for processing. So we are actually seeing here two levels of operation, one that takes care of capturing the stream or receiving the stream, or in the case of the direct model, just fetching the data from the external source, and then scheduling those operations on top of the data that we received to produce some result that can be exported or consumed by an API, put on a database, etc. We can simplify this model into we have an input, we have a process, and an output. Very simple. The input is represented by the D streams. The process are the transformations, is the API on top of these streams that is offered. And the output is materializing all those transformations into a result. A quick summary of operations. I'm really not going to touch into that. We have some stateless transformations, like map, flat map, unions, and joins. We have stateful transformations that are a little bit more complex. And important point here to keep in the back of your head is that many of those transformations are mapping down to the RDD API. So when we say DStream.map, what we're saying is that at each point in time when I have a bunch of data, apply, please, Spark this map operation to my incoming data in the form of an RDD. Oh, I think I have water. All right, so we have stateful operations. Transformation is very important because it gives us access to two levels. We have there the Spark, the Spark level, represented by the RDD, and the Spark streaming level represented by the transform operation. So we get here access to what I call the two-level scheduler. We can get operations running on the driver using the transform operation, and operations distributed across the cluster using transformations on top of the RDD. This is going to be kind of the key across the different techniques because it's a combination of these two modes of scheduling things and executing things, some of them on the driver, some of them on the cluster, that are going to give us the ability and the facility to create, let's say, more opportunities to program or use case in Spark streaming. Then we have actions. Actions materialize all the transformations. As we know in Spark, most of the transformations, they are all lazy. And there is only at the point where we say, okay, we want the results from here, is that all the computation is actually executed in the distributed environment and we get the result. This is the materialization of the computation. In Spark streaming, we have just a few of those operations. And as it turns out, there we only have one because all the implementations of all this print and save as operations, they all boil down to applying for each RDD with certain closure. So if you go to the source of any of those, you will see that it always ends up in the for each RDD and an operation. So in a nutshell, with Spark Streaming, what we have a number of transformations that map down to the RDD API. Then we have a single transformation, this transform, that gave us access to the driver and to the distributed environment. And we have one output operation being the for each RDD that will be our wildcard to get access to all the facilities that we can get in the driver. We can have access to the session, we can have access to Spark SQL, to the Graph API, whatever, and then we can map that computations also on the cluster. So here this is a code example of how that plays out. When we use the for each RDD, there is some code that executes on the driver and some other code that executes distributed in your cluster. This is very important to understand because there are also some limitations on what you can do in the distributed environment as to what is executing on the driver. For example, all serialization issues that we all know from the past, they only appear when you are in the yellow area, in the warning zone, while in the green area you can actually play with mutability, play with different APIs, call external services, no problem, everything goes. Like I'm trying to do there, getting some alternatives from a REST server. All right, so that was pretty quick a refresher of what Spark Streaming is. And now I'm going to provide you with a number of techniques that use those little hook points that I just mentioned, that we have access to the driver, that we have access to the whole execution environment, we have access to the distributed system, and more importantly, we have access to the scheduler. We can hook things in the Spark Streaming scheduler so that it does things for us at certain points in time, always based on that streaming interval or multiples thereof. Okay, the first one is let's say we start simple. This is self-contained stream generation. And you will see this small drawing. I kind of try to represent the use case with here there are no external boundaries. There is nothing going in, nothing going out. It's just your pure function of the Spark Streaming that you are going to implement, probably to test something, probably to just apply an idea, get a prototype up and running really quick. And for that, we use a constant DStream. It's a programmatic facility in Spark Streaming that lets you give there an RDD, and you get a DStream out of it with the same values every time. And then directly we say we discard this thing because what do I do with the same values every time? Well, the trick here is it's the same RDD, but it doesn't have to be the same values. We can have RDDs of functions that are generating data. And using a Scala function here, it's small because it's abstracted out. You just need to know that this is a function that when you apply it, you get a record out of it. And what we are doing is creating an RDD of some n elements that contain the record function. And it's a little mind twist because I'm not creating data, I'm creating functions that create data. And then I'm applying that function every time on the DStream to generate my randomized data set. As you can see, this thing can run on its own in one JVM context, or let's say in your laptop, you're trying something, or on a notebook, and it will start generating data at the moment that you start your streaming computation. Then we define there, for example, our raw DStream as a constant input DStream using that sensor data generation that I defined before. And this, let's call it trick, can be then further applied to other areas. For example, enriching my stream. I have some external data set, and I want to use the data that is in that repository. Let's be in some Cassandra tables over there, or some Parquet file, and I want to join this with my stream as the stream comes in. I recently worked on an NLP pipeline where we are just applying this to have our features feature model working. So we load the initial feature model from disk, and we learn online new words as the words come by in our pipeline. So very useful. This comes from, let's say, real practice out there, and is in production. So what are we doing is defining our source of reference. In this case, it's a Parquet file. That Parquet file is loaded there at the first line, and then we're going to cache it. This cache is called. That's probably the way most people do, and they don't go further from that. So I have my data, but I can never update it. You have the second mode of operation where you don't do cache, and then on every iteration, all the data will be reloaded again from their source. And that's, of course, slows down your streaming operation. You can have actually the best of both worlds by saying, I'm going to refresh my data, but only once in a while. Let's say you know that you have your pipeline of taking new customers. And new customers are provisioned. The customers, or let's say we're talking about an IoT business, and they deploy new devices every day. So at the end of the day, you can run this and have the new devices loaded in your system. What we're doing here is using that constant input DStream to hook into the scheduler. And that is done using a window operation. So in my window operation, I say, OK, I have probably a 1 or 2 second interval. I don't want to do that reload, force that reload every 1 or 2 seconds. That would be the same as not using that at all. But what I'm going to do is say, OK, every 5 minutes, I will go and I will fetch that data again, and I will replace the reference to the data that I use to modify my stream as the stream goes by. So we see there that what we do is take that refresh this stream, and we use it not for the data, but for the trigger. We unpersist the previous version of the data that we had. We reload the data file, reference data file, and we cache it again. That's basically the cycle that we are doing there, kind of a flip-flop. Okay, I release my memory of what I knew. The old thing is cleaned up. I load it again, and I cache it again. And it will be doing that every 5 minutes. Okay, that works pretty well. You will see small peaks over time. So every 5 minutes, if you open your stream in the console, you will see every 5 minutes you will spend more time than usual because you need to apply or use some of your time in the interval to load the data. Therefore, we have another method. Maybe you want just to refresh the data when something happens. And that something is coming probably through a stream as well. So maybe you want to dedicate a specific topic in Kafka to send notifications to your streaming operation, to your streaming job, that now I got a new customer onboarded, and I added maybe 1,000 or 1,000,000 new devices. Please load the reference file. Or I got a new account, and it needs to be reloaded in the system. Here we do it a bit differently. What we are doing is transforming one DStream into another. We are reifying the DStream. Okay, so the initial DStream is completely empty. It's that refresh DStream that it will only get one message once in a while. And I'm going to transform that stream. I'm going to actually use it to piggyback all the data that I got in my reference file, and I will create a much larger stream as an output of this operation. This could be also combined with the previous model where we don't use transform, but we use for HRDD, and then we use the reference data file. There is a minor point here, is that we are actually transforming our data frame or data set that we got from the initial Parquet file, and we are transforming it back into an RDD, and it will make your downstream operations then have to retransform this. Probably you would like to do this on a for HRDD instead of a transform. But the pattern will be exactly the same. You will just capture the trigger from your stream, and you will do the persist and persist flip-flop to reload the data. And I've been talking about structured streaming. We know this is based on the Spark SQL Catalyst and all the new abstractions like data sets that are being applied, sorry, I'm losing my voice, and being applied to, yes, oh, there is water there. Where? Oh, amazing. Thank you. Yeah, I have to get it open also. Okay, so we have scenarios of migration. We know our companies, they don't want to jump from one day to the next to the first shiny best thing that comes into the market. Sometimes we want to try things out and then have the opportunity to move forward and migrate everything or stay in the technology that we know already. Amazing. Okay, I think I can talk again. I was feeling like I was 15 or something, changing my voice. This is a pretty neat technique of having that portability between Spark streaming and structured streaming at the level of data sets. So again, we're playing here with duality of function and data, and we are defining our model or operations at each step of our pipeline as being a transformation from one data set of a type into another data set of a different type. Keeping here the types information is crucial because it will guide you on what you're doing and what each of the functions is providing you in the whole pipeline, and it will be a lot easier to connect one to the other. And then we can see there I defined parse, process, and serialize. This is taken from a real-world job that has been anonymized to protect the innocent. And Spark streaming, what we do is we create or input DStream. We create a data set out of this RDD that is there. So the source of the data is exactly the same. You can actually plug the Spark streaming version and the structured streaming version to the same data source using that model. And what we are doing is then composing functionally every step. We're doing their parse and then process and then serialize. That defines my final transformation function. And I apply that final transformation function to the oncoming data. That's on the Spark streaming. On the structured streaming, I already have a streaming data set to start with. So all I have to do is have my transformation pipeline. I build it up again there. And I do this because that also facilitates a lot of testing. Then when you want to go doing unit tests, what you want to do is provide a data set of a string to the parse. You need to get a data set of record, etc. The same thing for process and for serialize. All right, so that facilitates programming. It gets you in a, let's say, in a good design model where things are modular and can be replaced, switch one for the other. And you can also have like a feature parity or, let's say, the ability to be portable between Spark streaming and structured streaming. Some things will not be supported in one or the other. For example, windowing will be supported on Spark streaming, and on structured streaming, we cannot have anything that materializes the data set, like RD2 RDD or something like that, because it will not work. But in general, when you stay at the level of the general data set API, that works pretty well. And I'm going to accelerate a little bit because I think the clock is going faster backwards or something. Keep arbitrary state. This one seems very simple and is deceivably evil. What we are doing is we define a baseline again. We load this from somewhere, some file. And I want to add the data that I receive. And I want to expire some of that data. This is actually what the stateful models are doing behind the scenes. They are somehow keeping the data that comes in some internal structure and then applying some eviction policies to that. But in this case, we want to do this ourselves because, let's say, the provided APIs that don't give us all the facilities. In this case, I have features. I need to keep the new incoming features and adding it to my model. And some of them expire after a while, so I want to check which ones are expired. Also, the compare function might not be using IDs, but might be doing, let's say, matrix similarities between all the data. So you want really to keep as much data as possible, and then filter out some at some point. Why I say it's evil is because once this thing starts functioning, starts running in the background, Union starts keeping history, starts building up all the dependencies of the previous RDDs, of the previous stages that have passed over time. So this is the first time of this iteration, the second time, the third time, the fourth time, and then you get the picture. It starts exploding. So when you want to keep that level of history and that, let's say, programmatic facility to deal with the stored state in your stream, you also need to take some power or some burden on your own hands, and you need to roll out your own checkpointing facility. Spark streaming delivers you checkpointing, structured streaming delivers you checkpointing for the operations that are built in, that are supported by the model and the API. When you step out of that model, like I'm doing here in this case, trying to keep my own state, my own model, then it's kind of burden that we need also to keep track and keep checkpointing the data into secondary storage and reloading it every time. It's really first to be able to recover, because that's what checkpointing delivers you in the streaming model. But second, and more important, is to break that lineage from time to time so that it does not explode, and at the end, it will not be able to run. Okay. Last but not least, probabilistic accumulators. Accumulators have kind of a bad rep in Spark because they are not like behaving properly in some scenarios. Some of them, when it's a failure, and that failure, the task is relaunched again, some of the accumulators might count twice things. But if we join this accumulator with some probabilistic data structure, then we might be able to actually get rid of that downside of the accumulator by complementing it with a property of this probabilistic data structure. Really a quick introduction on why we want to do probabilistic data structure. So this is like the compromise, the tension between the exactness, real time, and big data. Let's say you have big data and you want to have real-time results, and you have to compromise on how exact your results are. You need to start approximating. Probabilistic data structures are giving you that facility, are giving you the tools to keep track of large amount of data, to answer questions on those very large amount of data by preserving using small data structures. This is really compressed. In this scenario, I'm going to talk about hyperlog that is giving you an estimation of how many different things we have seen over time. This is a classical question. How many users have we seen the past 24 hours that are unique? How many devices have we managed this last hour? Those counting uniques will require you to keep track of every ID that has passed through the system, which is burdensome. Using hyperlog, what I'm comparing there in these three spheres is the input data, so that's, let's say, gigabytes of data that are coming in. You need megabytes of data if you want to track unique IDs using some classical methods like keeping a set of every element you have seen, of keeping a map of every element you have seen. And this small thing here is what a hyperlog representation of that same megabytes of data would look like, 2-3 kbytes. All right? This is a strong tool to combine with your streaming applications, because streaming needs to work 24/7. You don't want to have any application that has increasing memory requirements over time. So let's say you throw more devices as this megabytes bulb will start growing, while my representation of the hyperlog will stay pretty much the same size. The combination, this is at the API level, we are going to wrap this probabilistic data structure into an accumulator V2, that provide better characteristics, better runtime warranties in Spark than the original implementation. And we need two operations, add and merge. accumulators work just like reduce in Spark, right? You are going to count things in every executor, 1, 2, 3, 4, 5. When I have my result in executor, I'm going to merge with the results of the other executors, and my final result will be the aggregation of all those. So it's a basic reduce operation. What we have here is a definition of that reduce operation. How do I add a new element to my accumulator, and who do I merge two accumulators together? There is a full implementation in the website where we put the code of the book. You can access it and use it for your own purposes. All right, and then once we have that accumulator up and running, then it's very easy to plug into your streaming job. First, you declare the accumulator. In that case, you create the HLL accumulator. You register it in the context. And then on each loop, you really need to add every user or every item, every data item detail that passed through. You add it to the accumulator. At the end, there we have, in the context of the driver, we can get the result, and we have the unique count over all the elements in that stream at every interval of time. You can accumulate that over time, and then you have answer from, let's say, from 1 hour, 1 day, et cetera, et cetera, et cetera. Okay, and just to put it all together, what I want to say as closing words is those are techniques, are tools that you can pick and use whenever you want. I give you options how to move into a structured streaming from your current Spark streaming implementations. How to improve the way you use memory with probabilistic data structures, how to load reference data on different ways that are the default provided when you use Spark Vanilla. And I hope you take any of those back home and use it in your next project. Thank you very much.
Yeah, that was a great talk. Thank you. That was a lot of depth, which I really appreciate, because it really shows, yeah, you're able to compare the two engines really easily, but also show how people can move between them when you need to. And so I really enjoyed that. Yeah, we have time for a couple of questions. We're sort of up here at the end, but we can go for a couple minutes. So if you have a question, please step up to one of the microphones. I got a question until someone walks up.
All right.
How often do you see the pattern of being able to switch between the engines, right? Of being able to do Spark streaming, et cetera, with your function and then process and then apply, et cetera. Mm-hmm. How much have you used that? What sort of has been people's reaction to that when you sort of share that with them?
Mm-hmm. So you are talking specifically about the migration pattern to a structured streaming. I have used it in a recent project where we wanted to use structured streaming, and we build up on top of that pattern. Right. It simplifies the way you think about the pattern. So I was working with a team of data scientists, and they tend to put everything in one large block of code. Yeah. And this helped me help them put things modular and then try it out in structured streaming and in Spark streaming. Very cool. So for one of them, we ended up doing Spark streaming because we needed to do learning on the fly. We were training a typical TF-IDF model, but we needed to keep track of the new vocabulary that was coming in. Yeah. But we had some other more ETL-like operations that were implemented using that model. Gotcha. And they let us quickly test one or the other and see where was the best fit. Gotcha. It's very practical, and actually from, let's say, a software development practice, it's a very neat way to test things as well. Yeah. Because you have, like, this is my input, this is my output, and there is how I'm going to test it. I just need to give some input, and this should be really delivering some output. Right, so basically you optimize for flexibility in a sense by doing more of the low-level RDD kind of thing, yep. And then that allows you to sort of hop between, and then you can sort of choose what's best at that given moment. Okay, cool. Okay, great. Let's give them a hand, and then we'll have a couple-minute break, and then we've got another one. All right. Thank you very much.